Hello, my name is Saeed Tabatabai, and welcome to my glider report. I decided to name my glider the UBJ Mark II, which stands for Unbalanced Balsa Glider Mark II, due to the fact that the wings kept breaking apart during the testing phase. The objective of this project was to design and build a glider using the material learned from class lectures and our own research. The glider was meant to be designed in a way that it would pass the 20 feet target. The overall aim of the project was for us to implement the designing knowledge we acquired to a real-world project such as a glider. The requirements of the project are as follows. The glider must fit in a 16 by 16 inch space. The glider needs to remain intact throughout the duration of the flight. It also needs to be hand thrown without the usage of any throwing devices. It cannot be controlled remotely, and it needs to show stability as it's reaching the 20 feet target. In addition to that, since I'm not a remote student, the glider needs to be made mainly out of balsa wood. The UBJ Mark II had met all the requirements mentioned previously. The dimensions of the glider fit in a 16 by 16 inch space. The glider was hand thrown without the assistance of any type of propulsion/remote control. The glider did achieve the 20 feet goal without shedding any parts on the final throw, and lastly, the main components of the glider were made from a thin sheet of balsa wood. Ideally for the wings, I needed a wing shape with a high aspect ratio to get higher amounts of lift. My choice was between rectangular wings, tapered wings, and elliptical wings. Each wing has its own unique properties that can have a tremendous effect on the stability of the glider. Rectangular wings are easier to manufacture compared to the other kinds due to the simplicity of their shape. Counteractively, the same simplicity makes rectangular wings induce high amounts of drag and stall characteristics. In my research, I found out that for gliders, the best wing shape is elliptical due to the fact that it minimizes drag. On the other hand, it is more difficult to manufacture with accurate dimensions compared to the other two types, and if a stall occurs, it occurs simultaneously across the wing. Due to the dimensions and the weight of the glider, elliptical wings were not a good choice either, since small gliders are more inclined to stall. Lastly, tapered wings induce less drag than rectangular wings and are easier to manufacture and have stall characteristics if they don't have washouts. I decided to go with the tapered wings since it seemed like it would fit my requirements. For the adhesive, my choices were masking tape, wood glue, and Gorilla super glue. I needed my adhesive to be as strong as possible since balsa wood can be broken apart easily. Masking tape is easy to work with and it does not add large amounts of weight to the glider. But unfortunately, it lacked in the strength needed for the glider to fly without breaking apart or have moving parts. Wood glue was much stronger than the masking tape, and it also made the glider more sturdy. The downside was that the wood glue takes hours to cure, and I simply did not have enough time for that. I decided to proceed with the super glue since it was the strongest adhesive in the list, and it dried fast. Super glue came out to be harder to work with than I thought, but the strength advantage was worth it. This just meant I needed to be really accurate with my placements. Since I was not sure about the placements of the parts yet, I decided to make my prototype using masking tape and the final design using superglue. For the dihedral angle, I needed to optimize the stability of roll and minimize the induced drag. My choices were 0, small, and large angle. According to my research, a small dihedral angle is sufficient enough to stabilize roll. It also produces a lesser drag than a higher dihedral angle. I needed my aspect ratio to be as high as possible, so I chose my wingspan to be 16 inches since it was the largest dimension allowed. After I did my research on the topic, I decided that my glider would be 10.4 inches long and 16 inches wide. The aspect ratio of the wings came out to be exactly 8, which was a good sign. The wing was placed 2.5 inches away from the tip and the tail was placed at the end of the fuselage. The areas of the horizontal and vertical stabilizers were also chosen according to the research and specifically in paper from MIT. The UBG Mark I was made using a cereal box, a straw for fuselage, and masking tape. The dimensions of the prototype were the same as the final design. Because of the cereal box cardboard being thin, I had to add joints to both sides of the wing so it maintains the dihedral angle and the winglets. It was the time for a test flight. After implementing small changes such as adding a toothpick in the tail for strengthening or adding the joints, the glider became sturdy and stable during flight. The UBJ Mark II was born. During the testing phases, the wings kept breaking, so I had to implement a change. I decided to modify a piece of wood by carving 3 sides into it so it would attach to both wings and to the fuselage. I also decided not to implement the winglets since I was worried about the glider breaking again during testing. In addition to that, I used sandpaper to make the fuselage more aerodynamic and also lighter. My center of gravity came out to be 3.35 inches away from the tip after I put the Play-Doh as the weight for the nose, which was only 0.1 inches away from the quarter core. The center of pressure is shown in green and the center for gravity is shown in red. After that, I got my angle of attack using an online tool. I calculated the lift coefficient for a thin airfoil using the above formula, which came out to be 0.05495. Then I proceeded to calculate the drag coefficient using the drag coefficient formula and a graph for efficiency ratio of a tapered wing, which came out to be 0.0138. The design changes I made earlier resulted in a much more stable glider. I had managed to stabilize the roll of the glider as well as the longitudinal stability. It also met all the requirements of the project as it flew for 30 feet without breaking apart and was stable during the flight. Overall, the project was a great success. We had to use the knowledge that we learned from this class and our own research to make a real-world design that would meet the requirements of this project. Further improvements can be done by adding winglets, using a flat-bottom airfoil, and adding a thin layer of plastic over the majority of the glider to reduce the induced drag. I'm happy with how this project turned out to be. It taught me how to apply design concepts within the real-world limits and how to meet the requirements of a project.